All right, I want to explore spherical coordinates a little bit. So first I want to take a look at what surfaces are created by fixing each of the spherical coordinates. And then I want to go ahead and do the work to set up a triple integral over a region in 3 dimensions that is expressed using spherical coordinates. So it's sort of the same thing that we did for cylindrical coordinates, but well, obviously in this new coordinate system. Okay, so first imagine that you are collecting together all of the points in 3 dimensions that have a row value of 2. In order to understand what that looks like, I have to remember what the row coordinate measures. The row coordinate measures the distance from the point to the origin. So I know that to be a sphere. It's going to be a sphere of radius 2. Just draw it like this. And you could see that algebraically as well if you wanted by recalling what rho is in terms of rectangular coordinates. So we know that rho squared is x squared plus y squared plus z squared. And so rho equals 2 would be converted to 4 equals x squared plus y squared plus z squared, which is exactly the sphere that I just drew. So in either way, we understand rho equals 2 to be a spherical equation for this sphere. Okay, theta equals pi over 4. Since theta in spherical coordinates is the same as theta in polar coordinates or cylindrical coordinates, I'm going to get the exact same surface that I did in cylindrical coordinates. So this right here, this plane that makes an angle of pi over 4 with the positive x-axis is exactly all of the points that have a theta value of pi over 4. So nothing new there. Now finally the phi, this one's a little tricky the first time that you see it, but let's suppose that I tried to gather together all of the points in 3 dimensions that had a phi value of pi over 6. So all of the points that when I connect the point to the origin, that creates an angle of pi over 6. So like a point that I just drew kind of does that. But any point along this line would also do that, right? And then if I grab some points over here that make an angle of pi over 6 to the positive z-axis, those would lie on the surface phi equals pi over 6. And I can spin this around. So actually what I'm getting is a half of a cone. Okay, like this. Okay, and if I look at the conversion equations, actually I've copied the conversion equations down here for convenience again, I can obtain this result algebraically as well. So let's take a look here. If I take phi equals pi over 6 and try and imagine it in rectangular coordinates, let's take a look at what we get. I would get that z equals rho times cosine of phi. Well, cosine of pi over 6 is square root of 3 over 2, right? And what would we get for y? Y would be rho, oops, I've copied this incorrectly. Let me fix that. Okay, back to this. So y is rho times 1/2 sine theta, so that's 1/2 rho sine theta. And lastly, x is 1/2 cosine theta, rho cosine theta. Okay, so let's just observe what happens when I take the x expression and square it plus the y expression squared. Well, I'm going to get 1/4 rho squared cos squared plus 1/4 rho squared sine squared. Factoring out a 1/4 rho squared, I see I'm left with sine squared plus cosine squared, which I know to be 1. Okay, and with a little bit of algebraic trickery here, I see that this is the same thing as 1/3 times 3/4 rho squared, and that's exactly 1/3 times the z-coordinate squared. So that little algebraic manipulation has given me a Cartesian equation for this surface. So saying phi equals pi over 6 is the same thing as saying x squared plus y squared equals 1/3 z squared. And so that you can recognize as the equation of a cone. Okay, down here I've just sort of rewritten the conversion equations for converting in between any of the any two of the three-dimensional coordinate systems that I have here. So make sure you are familiar with those equations and know how to use them. So what I want to do now is develop the volume differential expression that appears when I set up a triple integral over a region that is expressed in spherical coordinates. So we did this with rectangular coordinates, we did it with cylindrical. With rectangular coordinates, the dv, the unit of volume, is simply dx, dy, dz, because when you chop up a region into a million pieces according to rectangular coordinates, you're just getting little what are they called? Rectangular solids with edges dx, dy, and dz. In cylindrical coordinates, I'm getting r d theta dz. And with spherical coordinates, we're going to get something else. So what we need to do to develop this expression is we need to imagine taking a three-dimensional region and chopping it up into a million pieces according to spherical coordinates. So we're taking the three-dimensional region and chopping up into so-called spherical rectangular solids. So let me get a drawing. And the way that I like to think about this is fixing a point in 3 dimensions and then making 3 small adjustments. First, according to the rho coordinate, then the phi coordinate, then the theta coordinate. Let's see what that would look like. So I'm standing here in 3 dimensions, and I'm just going to adjust the rho value slightly, all right? Well, I'm drawing it bigger so that I can see what's happening. So, increasing the rho coordinate means that you're going out radially from the origin. So this is what it looks like to move the rho coordinate away from this point. Now let's adjust the phi coordinate. That would mean that I am moving the angle towards the positive z-axis. So that's what it looks like to move a little bit in the phi direction towards the positive z-axis. And then finally, if I move the theta, then I'm going at an angle relative to the positive x axis. So let me try and build from this a sort of spherical rectangular solid that represents starting at this point and adjusting each of those 3 coordinates a small amount. Okay, so there you go. There's the image of a spherical rectangular solid. You can see it's not like a perfect box, right? That's because the angular coordinates here cause sort of curved edges to this thing. But the idea is that I take my 3-dimensional region, chop it up into a million pieces that look like this, and then I have to integrate over it. So as you know, with triple integrals, it's fundamental that I get the volume of such boxes relative to the coordinate system that you're in. So as you can see here, as I move out from the origin, these types of boxes get bigger and bigger and bigger. So there's going to be just some discrepancy between the volume of this box and just simply the delta rho, delta phi, and delta theta. All right, so I'm going to draw some more stuff that's going to help this computation. So I'm going to first start by drawing the shadow in the xy plane. So drop the point down to the xy plane here and observe that that movement in theta looks like this. Okay, so I sort of drop that shadow here. And let's label some of the distances that I have on the picture here. So this right here would be the delta theta, right? And then the original point had a rho distance to the origin, which when you drop the shadow, that translates into an r distance. That's r right there. And as with polar coordinates, we know that the length of this arc is just r times delta theta. So this arc right here is r delta theta. And I can see that arc up here. Of course, in spherical coordinates, r delta theta isn't r delta theta because r isn't a spherical coordinate, but I know what r is in terms of spherical coordinates. That's up here somewhere. Scroll up. R is the same thing as rho sine phi. So let's replace r with rho sine phi. And so this expression right here gives us an estimate for how long that arc is. Okay, let's do the other arcs now. Let's take a look at this one. So this arc is created by moving this point delta phi in this direction, right? So it's also a circular arc with angle this time phi and radial distance rho. So the length of that arc is going to be rho times delta phi this time. Okay, and lastly, the last dimension that I'm going to need to sort of figure out the approximate volume of this rectangular thing, spherical rectangular solid, which is sort of a ridiculous thing to name it, but that's what it is. This right here was our very small change in rho, like that. So look, the dimensions of this not quite perfectly rectangular solid are the quantity in red, the quantity in blue, and the quantity in orange, all expressed in terms of spherical coordinates. So from this, I extract the differential unit. So delta V is approximately, what do I have here? I'm just going to multiply these three dimensions together. I've got a rho from the red. I also have a rho from the blue, so that's rho squared. Then I have a sine phi, and that's what's left is a delta rho, a delta theta, and a delta phi. So delta rho, delta theta, delta phi, and oops. And then in my integral, so once you set up your Riemann sum appropriately with this delta v expression, you take your limit, you get your triple integral, which then has its differential unit looking like this. Okay, so whereas a triple integral in rectangular coordinates has some, dx, dy, dz, dv expression, and cylindrical has r, dr, d theta, dz. With the spherical coordinates, we're going to have our squared sine phi, d rho, d theta, d phi.